Okay, so before I forget to say, in general, next week you are supposed to have this short exam, but next week I will be shifting the short exams by 1 week. Next Monday we will have a lecture. The following week you will have a short exam and then 1 week lecture, 1 week short exam, because the following week, on the week of the 17th, I won't be here, so we won't have any lectures, but at least we can make use of that week for the short exam. So let's just first go over what we had done in our last lecture. So we were looking at, we had discussed this canonical ensemble where the probability that the system will be in a given state will be proportional to, will be given by e to power minus beta times the energy of that microstate. And we were looking at some applications of it. And we had seen that if you can calculate the partition function, the logarithm of the partition function gives you the free energy. And once you know the free energy, you practically know everything about your system. That was the basic idea. So we were looking at the partition function. If we have non-interacting particles, the partition function for n non-interacting particles is again proportional to the partition function of one particle raised to the power n, because if there are no interactions. And then we said, okay, let's look at this magnetic system. Let's imagine a magnetic dipole, which has a magnetic dipole moment given by mu in a magnetic field. What will be the magnetization, the magnetic susceptibility of this system, etc. Of course, we don't have pure magnetic dipoles, but we can think of this as a system of particles that are moving around, but they also have a magnetic dipole moment. If that is the case, we can practically separate the two degrees of freedom. The partition function will be basically the product of the partition function corresponding to the translational degrees of freedom times the partition function responsible for the magnetic degrees of freedom, of course, assuming that the translational degrees of freedom and magnetic degrees of freedom are independent of each other. In that limit, we can look at the magnetic properties separately. So the microstates of this magnetic properties will be given by the orientation of this magnetic dipole moment. Each different orientation would give us a different microstate. And summing over the microstates was essentially just integrating over the solid angle of the orientations of our magnetic dipole. And, well, then we looked at the low temperature limit, the high temperature limit. I had made some mistakes. We had corrected them. And so let's continue. Now, another problem that we addressed was systems with, so when we calculated the average energy of this system for a positive temperature, what we had seen was the low temperature and the high temperature limit of this system, At the high temperature limit, when T diverges, practically U is 0. At the low temperature limit, this was the case when all the magnetic dipole moments were aligned with the external magnetic field. Then we asked ourselves the question, what happens if all the magnetic moments are anti-aligned with the magnetic field? Such a system would have a positive energy, but we couldn't get this in this treatment. That is what led us to negative temperatures. You see, this expression we obtained in the high T, large T limit. Well, this expression would also be valid if T is very large but negative. That would give us a positive energy system. So that is what we call negative temperature systems. The negative temperature systems have a larger energy than positive temperature systems. And in fact, this was what you would get as U for the energy as a function of temperature. When the temperature is 0, all the dipoles are aligned with the magnetic field, giving you a negative energy of minus mu and b. When T becomes infinitely large but positive, then the energy is positive but slightly below zero, if it's finite but very large. If T is negative but huge, then the system has a positive energy. And you can go up to T equal to 0, but from below. That is the highest energy configuration. So that you can actually create such systems. You take, if you just consider, for example, the nuclear magnetic moments of a given solid. So you just align them with the magnetic. You lower the temperature. You put it in a very strong magnetic field. You lower the temperature so that the system, all the magnetic dipoles are aligned with the magnetic field. But then, if you flip your sample, all the magnetic moments will be anti-aligned. And of course, the reason why we are looking at the nuclear magnetic moments is that they weakly interact. The energy transfer from the nuclear magnetic moments to other degrees of freedom will be very slow. So for a measurable amount of time, the system will have a positive energy, which means it will have a negative temperature. But of course, although the interactions are slow, it's like the magnetic dipole moments of negative temperature interacting with a system of positive temperature. And this system of negative temperature eventually will transfer enough energy to the system of positive temperature so that its temperature will also be positive. But for a reasonable amount of time, we have a system of negative temperature. And basically that is what we had done. We had also looked at the spin 1/2 case, the quantum mechanical description for the spin 1/2 case. And well, there we had actually solved for how the temperature and energy are related. And the reason of negative temperatures, you can also tell it from this expression. If you look at the problem from the microcanonical ensemble, given the energy, you can calculate the entropy. There is one configuration in which all the magnetic dipoles are aligned with the magnetic moment. That is, there is one configuration which has an energy minus mu and b, and one configuration which has the energy is equal to plus mu and b. It's these two extremes. One is here, the other one is this one. So the entropy starts from 0 when the energy is a minimum. It increases, but eventually, if you keep increasing the energy further, since the energy has an upper maximum, the entropy starts to decrease. So that if entropy decreases with increasing energy, remember 1 over T is ds by du. If entropy decreases with increasing energy, that means the temperature is negative. So that is where we had left. Now today I intend to start a general treatment of this case, not just a spin 1/2, but an arbitrary spin. An arbitrary total angular momentum, let's say. It can have also the orbital angular momentum and the spin degrees of freedom. But any questions about what we had done in our last lecture? Okay, so this is our problem. We have a system. If you would consider the system, there will be a Hamiltonian corresponding to other degrees of freedom of your particles. You can imagine a gas of electrons, for example. The translation, and if there are any other degrees of freedom, they're all over there. The interaction with the magnetic field will be given by, again, mu is the magnetic dipole moment of whatever particles we have. But in this case, mu will be not just proportional to the spin, it will have a, let me write Q over 2m L dot B. Well, there is a component which is due to the angular momentum. You see, if you have a particle moving around, it will have an angular momentum, And since you can imagine it as a charge carrying loop, if you like, there will be a part proportional to that motion, corresponding to that motion. Do you remember what magnetic moment of a particle is? Let me ask you that first. Well, let's just remember it. A very simple, let's say that we have a point particle. It can be the electron orbiting the atom, for example. The magnetic moment in general is defined as the current times the area. This is the general definition. Well, the current is, let's say, it is going around an orbit, circular orbit with radius. Or let's say that the current will be whatever charge my particle has divided by the period of rotation times the area. The period, well, it is covering a distance 2 pi r during a time with a speed v. This is the period of rotation times the area, which will be qv over 2 pi r times a. This is the a is pi times r squared. This is the area of the loop. Well, the pi's cancel, r's I can cancel them. Which gives me q over 2m mv times r. mv is the linear momentum. This is q over 2m, p times r. But this is nothing but q over 2m, the magnitude of the angular momentum. Remember, angular momentum is p cross r. In this very simple model, let's say, my particle is moving on, carrying out a circular motion. This is the direction of p. This is r. No, sorry, r cross p. So the magnitude is just p times r. Well, the direction, just use your right-hand rule, the direction of angular momentum is out of the board. And the direction of the magnetic dipole moment, if there is a current running in the counterclockwise, if, let's say, Q is positive, then this current is running in the counterclockwise sense. Again, your right-hand rule tells you that mu is also out of the screen. So mu is, as a vector, is q over 2m times L. This is for a simple system of a single particle carrying out uniform circular motion, but this expression is quite general. So if you have an arbitrary, if you have a particle that is moving around, which has an angular momentum L, its magnetic dipole moment is q over 2m, which is called the Bohr magneton, times L. If the particle has spin, spin is just like the angular momentum, so you would expect it to have the identical dependence. But it's not identical. There is a factor 2. Spin is weird. It behaves similar to the angular momentum, but not exactly similar. The interaction of spin with a magnetic dipole moment has an extra factor of 2. Now, this factor is, by the way, predicted by the Dirac equation. So if you have seen the Dirac, have you taken 508, quantum mechanics 2? Yeah, you don't. At least there is a derivation of this factor 2 in quantum mechanics 2. It's not something we just put by hand. It's predicted by the Dirac equation. In fact, we can even calculate the corrections to this factor 2. And in fact, for electrons, we had calculated and measured this correction to this factor 2 up to, I think, 13 digits, 13 or 15 digits. So the magnetic part of our Hamiltonian is minus QB over 2m Lz plus twice Sz, assuming B is equal to whatever magnitude it has in the Z direction. Now, if each other has rotational symmetry, let's say that it has rotational symmetry. Well, what rotational symmetry tells us is that we can write the energy eigenstates in terms of the total angular momentum, quantum number, Jz, L, and S. You see, in our last lecture, we just looked at a spin 1/2 particle. We ignored the angular momentum. If there is no angular momentum, then J is just equal to S, so we only have S and Sz. But now, for a general system with rotational symmetry, the total angular momentum will be conserved. So that's what the J corresponds to, the total angular momentum quantum number. Jz is the Z component of total angular momentum. And the total orbital angular momentum, the magnitude is conserved, and the magnitude of spin is also conserved. Now, what we can do is, we need to calculate Z. Okay, sum over all microstates of e to power minus beta e. We need to know the energy of my system. Well, without knowing what the H is we cannot really calculate the exact energy eigenvalues, but one thing we can do is we can look at the first correction. The first correction to the energy, first order in perturbation theory. Will be given by J, Jz, Ls, Hb, J, Jz, Ls. This will give us what the first order correction is. I will not go into the calculation of that. This will be minus G mu B. Well, it's just like the previous case. Mu B, well, there was also the cosine theta. And let me put Jz here. No. This G will depend on J, L, and S. And J, sorry. That J is also there. This is the matrix element. This G is given by 3/2 plus S plus 1 minus L plus 1 divided by J plus 1. Okay, let's consider several cases. For example, if this were, we didn't have any angular momentum, then HP will just have special cases. L is equal to 0. We can look at systems with only a spin. Then J, Z, L, S would be just SZ states. The Hamiltonian will be minus 2 mu Z SZ. And this energy will be minus 2 mu Z MZ. MS. Well, let's see what we get over here. G. J is S, 0, S. This is equal to 3 over 2 plus S, S plus 1 minus 0 divided by S, S plus 1. This is equal to, this is 1. This is 5 over 2. I might have a factor 1 over, oh, sorry, this is 2jz, 2jjz. So this is 2. It does reduce to our expression over here. There's G in this limit, in this case, G is just 2, as it should be. Anyway, this is the quantum mechanics part. So let's just take this result. Take this result. This is our energy of the system. Energy due to the magnetic degrees of freedom. So what does this tell us? The partition function, sum over all microstates of e to power minus beta e, sum over all microstates of the exponent of beta. Well, this is our e. This is my e. There's a minus sign over there. Beta mu b mj. Now, the microstates for a given j will be just given by mj. If I know mj, I know the microstates. So the sum over microstates for the single particle will be sum over mj, that k takes values between minus j to plus j, of exponent of beta mu b g raised to the power j, raised to the power mj. Okay, what is this sum? How do we calculate this sum? Okay, so this factor over here is independent of j. Independent of mj, sorry. I'm summing over mj. It is basically sum of m from a to b x to the power m. You see, when you don't remember these, and I also fail to remember these expressions, it's easy to calculate. X to the a, x to the a plus 1, x to the b. The trick is just multiply this by x. This is the sum I'm looking for. Multiply by x. This is x to the a plus 1, x to the b plus x to the b plus 1, and subtract. So you get x to the a minus x to the b plus 1, because when I subtract, these terms will cancel. I will be left with x to the a and x to the b plus 1. This is 1 minus x times s. So sum a from a to b, x to the m, is actually x to the b plus 1 minus x to the a divided by 1 x minus 1. Okay, so let's apply it over here. My partition function is exponential of beta mu b g j plus 1. You see here, the next term. The first term that is not the term after the last term in the sum, minus the first term in the sum times j divided by whatever that factor is, minus 1. This is my partition function.
Isn't that minus j?
Hmm?
Isn't that minus j? The first one.
Where? This one.
First summation of the series. Second term, minus something.
This one. Oh, sorry. You are saying that A is minus J. You are right. So this is minus J. Thank you. Because Mj, the last value it takes is J. The next term is J plus 1. And the first term that Mj takes is minus J. So that's why in the first exponent I have a minus 1. Now let's try to write it in a slightly different form. Let me write it in this form. In the denominator, let me take beta mu b g over 2 out. So that it became now sine hyperbolic. Let me take the same factor from the numerator out. Well, these factors cancel. What remains is just the ratio of two sine hyperbolics. Now, let me define x to be beta mu b g j. So the partition function, this is of course for a single particle, will be sine hyperbolic x times 1 plus 1 over 2j divided by sine hyperbolic x plus 2 x over 2j. Now I can calculate all the properties I want. Let's start with the energy of the system. Remember, the partition function of the whole system of n magnetic dipoles is Z1 to the power n. The energy of n dipoles was minus the derivative with respect to beta of logarithm of z, which is minus n times derivative with respect to beta of logarithm of z1, which is minus n derivative with respect to beta of logarithm of sine hyperbolic x1 plus 1 over 2j minus logarithm of sine hyperbolic x over 2j. The beta dependence is through x only. This is equal to minus n derivative with respect to x, which will give me, let's see, 1 plus 1 over 2j times cosine hyperbolic x 1 plus 1 over 2j. Let me write it cotangent hyperbolic. It will be cosine hyperbolic over sine hyperbolic minus, well, the same thing over here, 1 over 2j cotangent hyperbolic x over 2j times derivative of x with respect to beta. Well, remember the definition of x of here. This is my definition of x, so if I take the derivative with respect to beta, that would give me mu bg times j. Times all that 1 plus 1 over 2j so this is the energy of my system. I will not do the other derivation, you see. The difficult part over here was, what is the energy, eigenstates? Okay, before we always dealt with systems in which we could identify the energy exactly, but if you have both angular momentum and spin, well, we don't have the exact energy. Nevertheless, we can use perturbation theory to approximate the energy. This is our energy, approximate expression of the energy. The contribution to the energy from the magnetic field. And once you identify the energy, the rest is more or less straightforward. What you do is you just first go ahead and identify the microstates, calculate the partition function. Once you have the partition function, you just take various derivatives. And that gives you the energy. In this example, then we could calculate the magnetization if we take the derivative with respect to the magnetic field. Once we know the magnetic field, magnetization, just taking its derivative with respect to B again at zero magnetic field would give us the magnetic susceptibility. I'm not going to do that because we basically did that for spin 1/2 system. It's just some expressions will be slightly different. And the high temperature, low temperature limit will practically be basically the same. At least the method will be the same. The results will again be slightly different. You see, in this case, the high temperature or low temperature is determined by, remember, X is beta mu B J. So high temperature basically means beta is small. That means X is small. Low temperature, X is much, much larger than 1, which basically means that KT is larger than mu Bj, or KT is less than mu times B times J. Remember here, mu times J is the magnitude of the magnetic moment of this system. If you would look up in your notes or in your book and compare it with the other result, with the classical result we studied, You see there, if you identify mu times J with the classical magnetic moment with different orientation, well, that is what we should also do over here. The magnitude of the magnetic moment is mu times J. There's also G mu times J. If J is large enough, you practically recover the classical result. That's also another application of the classical correspondence. I mean, in your quantum mechanics courses you should remember at least, if you go to large quantum numbers, you should recover the classical limit. So here, the large quantum numbers will be the log J. You should identify mu J times G as the magnetic dipole moment of a single dipole. And when J is very large, these terms, 1 over 2 J's, practically they will go to 0. And you go back to the classical result. Well, it's kind of easy to take let's say, the low t limit. I mean, even in this case, low t, x is very much larger than 1. Then cotangent hyperbolic x over 2j will be huge. In that limit, cotangent hyperbolic just becomes 1. Energy in that limit at the low temperature becomes minus n mu b g times j 1 plus 1 over 2j, cotangent hyperbolic is 1, minus 1 over 2j. Again, cotangent hyperbolic is 1, these cancel. Well, basically all the magnetic moments are aligned with the magnetic field, even in this case. So any questions in these derivations? Any questions about the canonical ensemble? So if there are no questions, let's give our 10-minute break a bit early, because in the next hour, I will start the grand canonical ensemble. Now, basically, we will repeat more or less what we had done in the microcanonical and canonical ensembles, in a case where we also allow the number of particles to change. Let's give a break, and we will continue after the break.